Beneath the crushing darkness of the abyss, a silent fireworks display erupts every second. Tiny organisms turn chemistry into light, turning the deep sea into a living lantern. Bioluminescence starts with a tiny molecule called luciferin. When luciferin meets the enzyme luciferase, it oxidizes, releasing a photon. The reaction can be written as luciferin plus O2 oxyluciferin plus light. In many fish, the substrate is choline, while bacteria use FMNH2 and a long-chain aldehyde. The energy of each photon depends on its wavelength. A blue photon at 470 nanometers carries about 4.2 times 10 superscript 1 joules. Some organisms achieve quantum yields above 80%, meaning most of the chemical energy becomes light. Photoproteins, like the jellyfish protein aquarin, bind calcium and release light instantly, allowing rapid flashes. The reaction is temperature independent, so it works at the 2 degrees Celsius temperatures found at 1,000 meters depth. This efficient chemistry lets a single cell emit enough photons to be seen from meters away, a crucial advantage in a world without sunlight. Water absorbs light like a filter, but not all colors are equal. Blue and green wavelengths, for 170 to 490 nanometers, travel the farthest, losing only about 0.04% of intensity per meter. Red light at 650 nanometers is absorbed within the first 10 meters. Because of this, 75% of deep-sea bioluminescent species emit blue-green light, matching the ocean's transmission window. The dragonfish Malacosteus niger is an exception. It produces far-red light around 710 nanometers using a unique bacteria chlorophyll-like pigment, invisible to most predators but visible to its own specialized retina. Lanternfish of the family Myctophidae emit a narrow blue peak at 475 nanometers, which can be detected by eyes as small as 0.5 millimeters across. This spectral tuning maximizes visibility while minimizing energy loss, turning a chemical spark into a signal that can travel dozens of meters in the abyss. The classic anglerfish, Melanocetus johnsonii, dangles a bioluminescent esca at the end of a filament 10 centimeters long. The lure houses colonies of Photobacterium phosphorium that glow at roughly 0.1 candela, bright enough to attract prey from 2 meters away in the pitch-black zone below 1,000 meters. Dragonfish like Stomiidae line their heads with photophores that can be switched on and off in milliseconds, creating a strobe that confuses small fish. The vampire squid, Vampirotuthis infernalis, sprays a cloud of bioluminescent mucus when threatened, forming a glowing veil that obscures its escape. Some shrimp, such as Aplophorus gracilorostris, eject a luminous secretion from their mouths, a defensive ink that flashes for up to 30 seconds. These strategies rely on precise timing. The firefly squid Wattisenia sinolens can flash up to 60 times per second, each flash lasting only 2 milliseconds, a speed that rivals a camera's shutter. Midwater predators often hide by matching the faint downwelling light. The cookie-cutter shark, Icistus brasiliensis, coats its belly with photophores that emit a uniform glow of about 10 CD m superscript 2, the same intensity measured at 500 meters depth on a moonless night. Lanternfish, such as Myctophum punctatum, adjust each photophore's output in real time, dimming when a predator looks up and brightening when the ambient light changes with the surface. This dynamic camouflage is controlled by a feedback loop between the eyes and the light-producing organs, allowing intensity changes of up to 100-fold within seconds. Counter-illumination reduces the silhouette by up to 90%, making the fish virtually invisible from below. Some species, like the hatchetfish, also use a dark patch on the ventral side to break up their outline, a strategy called aggressive mimicry that tricks predators into seeing a harmless silhouette. Bioluminescence is not a party trick. It shapes entire ecosystems. Surveys of the Eastern Pacific show that roughly 76% of mesopelagic taxa emit light. compared with only 2.5% in coastal waters. This glow fuels a nightly vertical migration of up to 10 million tons of biomass, as lanternfish ascend to feed and descend to hide, their flashes guiding schools like a living lighthouse. The sheer abundance of light also interferes with scientific instruments. The Antares Neutrino Telescope in the Mediterranean records background bursts from bioluminescent swarms, sometimes increasing photon noise by a factor of 30 during seasonal blooms. Seasonal studies in the Ionian Sea found peak bioluminescent activity in summer, correlating with higher plankton concentrations. In short, light is a currency in the deep sea, traded for food, mates, and safety, and its physics reverberates through the food web and even our technology. The abyss still hides countless luminous mysteries. Next time we'll explore how crushing pressure sculpts the anatomy of the deepest dwellers. Subscribe and hit the bell so you don't miss the next deep sea revelation.